This is the screencast for section 9.1, example 5. So just like we have term-by-term differentiation, we also have term-by-term integration. So if you have a function and its series, you can integrate that function and integrate its series to find two equivalent statements. Now that also implies that if the antiderivative of some function is a different function, then the antiderivative of the power series for that original function is also the power series for that other function, which might come in handy in a couple minutes. So here in example 5, we're going to find the power series by integration. So given that 1 over 1 plus x, its power series is the following, which you saw in Exploration 1, Part 1. Find a power series to represent the natural log of 1 plus x. So I don't have anything here with natural log in my given statement, although I do know that the antiderivative of 1 over 1 plus x dx does equal the natural log of 1 plus x, then plus a constant. So because the antiderivative of this function equals the natural log of 1 plus x, I can find the antiderivative of both sides of this equivalent statement to get the power series for the natural log of 1 plus x. So I'm going to start out with that statement in terms of t, and I'm going to integrate both sides of that statement from 0 to x. Which means then, on the left side I'll have the natural log of 1 plus t evaluated from 0 to x. So there's where I'm going to find what the power series is for natural log of 1 plus x by integrating the right side, this power series. So if I integrate the 1, I get t, integrate t, I get 1/2 t squared, etc. This pattern looks like it's following, let's see here, -1 to the n, and then t to the n plus 1. So this was 0, its exponent is 1. This is term 1, its exponent is 2, etc. And then we're dividing by that same value, so n plus 1. Now that also needs to get evaluated from 0 to x. Now both sides of this statement, if you plug in 0, you get 0, so I really don't have to worry about that in doing the fundamental theorem part 2. I just have the natural log of x on the left and its power series on the right by integrating the original statement I was given. Now the interval of convergence is going to stay the same. We didn't really change that at all in the integration process. And I'm going to look at Wolfram alpha to see if I'm right. So I got the series expansion to be the same thing, yep, that I see here. And then here's the approximations, and it does look like it's converging from -1 to 1. And of course, with the more terms we add to so order 4 this is only up to. If we go to order 20, it's going to look a lot more like the original curve between -1 and 1. Then I'll try problem for number 5 in the book was horrible. So I made up my own here. We're going to integrate from 0 to x 1 over 1 plus t squared this time dt and its power series. Well, first of all, 1 over 1 plus x squared's power series is this lovely function. We're basically replacing x with x squared as we did in example 5. Little simplification, and now I'm going to integrate both sides of the statement. So I put both sides of the statement in terms of t, and now I'm going to integrate from 0 to x, both sides. So this left side is not a natural log anymore. You should see this as an actual inverse trig. It's inverse tangent of t, and we're going to evaluate that from 0 to x. And then term by term integration here is going to result in t minus t cubed over 3 plus t to the 5th over 5, etc. And we could write what pattern that's looking like it would be. I'm just going to do that in the next step. So I have the inverse tangent of x. Again, inverse tangent of 0 is 0. If I plug in 0 on the right side, those are all 0, so I don't have to worry about that term. But if I plug in x, I get these first 4 terms, and that pattern is -1 to the n. X is being raised to the 2n plus 1 power. So here, x is to the 0 power. I'm sorry, x is to the first power, but this is the 0th term. So that 2n plus 1 still works. Now we have the third power for the first term. So 2 times 1 plus 1 is 3. 2 times 2 plus 1 is 5. 2 times 3 plus 1 is 7. So we got that 2n plus 1 divided by that same value. Now if we write that in summation notation, we have the sum from n equals 0 to infinity of negative 1 to the nth power of x to the 2n plus 1 over 2n plus 1. Again, that is going to have the same interval of convergence, and that's just because you're replacing, like we said, x squared with x, and if you evaluated negative x squared is less than 1 and positive x squared is less than 1 to get rid of that absolute value, you'd find the same interval of convergence.